The definition of a rational function is that it is a ratio of two polynomials. Therefore, it is something of the form p of x over q of x, where p of x and q of x both satisfy the definition of a polynomial. Remember that a polynomial is a sum of terms of the form ax to the n, where n must be a whole number. That's the main restriction that we have on the definition of a polynomial. So that power has to be a number like 1, 2, 0, 1, 2, 3, etc. We can't have any fractional powers. We can't have any negative powers in a polynomial. So looking at our first function here, f of x equals 2 over x minus 1. 2 is the same thing as 2 times x to the 0, because anything to the power 0 is equal to 1. So this is a degree 0 polynomial on top. And x minus 1 is a degree 1 polynomial. So we would say yes, this is in fact a rational function. Because it's a rational function, we will find the domain. And the way we find the domain of a rational function is always the same. We just take the denominator, x minus 1 in this case, and we say that that denominator cannot equal 0, because that would give us a division by 0 error. So if x minus 1 can't equal 0, then that gives us an equation that we could solve to find out what x cannot be. Adding 1 to both sides, we can see that x cannot equal 1. I can also put this in set builder notation, writing this as the set of all x such that x is not equal to 1, because a domain is a set of numbers. Going on now to g of x right below, we have in the denominator a degree 2 polynomial, but in the numerator we can see the square root of x. Even if I were to rewrite that as a power, that power is 1/2. That would be written as x to the power 1/2. So even though I can write the square root of x as a power of x, it is not a whole number power. And therefore we would answer no to this one, and we will skip the domain question for this because it is not a rational function. Next, we will come back up to the top for h of x. We have a degree 2 polynomial on top. We have a degree 2 polynomial in the denominator as well. Both of those are polynomials, and therefore this does satisfy the definition of a rational function. So to find the domain, I'm again going to focus on the denominator, pull out the denominator, and set it not equal to 0. It's okay to just set it equal to 0 and change it to not equals at the end, but I find that sometimes students forget to change it to not equals later, so I just do it from the very start. That the idea of the domain is that this whole denominator cannot equal 0. That way all I have to do is finish solving in order to get my domain. This is something I could solve by factoring very easily. I factor out a greatest common factor of x, and then in the next step I set each factor not equal to 0. So I see that x cannot equal to 0, and x minus 3 also cannot be equal to 0, which gives me that x cannot equal 3. So I could write this as x is not equal to 0 and x is not equal to 3. I'm going to change that and to an ampersand here to make it a little more clear. And I can put set builder notation on this saying this is the set of all x such that x is not equal to 0 and x is not equal to 3. Finally, I have just a polynomial. I can actually consider this a rational function by converting it to a ratio by putting it over 1, the same trick that we do with fractions. Now I can see that the numerator is a degree 2 polynomial, and the denominator is a degree 0 polynomial. So this is actually a rational function. For finding the domain, however, I see right away that as I grab my denominator and set it equal to 0, or not equal to 0, and I say 1 can't equal 0, right? That doesn't actually give me any restrictions on x. That's a statement that's always true, so that's great. This means that my domain is actually all real numbers, because setting the denominator not equal to 0 did not give me any additional restrictions. So one way to think about domain of a function that's defined symbolically is that you start out with a set of all real numbers and you say, I'm only going to remove values if they cause problems. In this case, the problem they would cause is division by 0, which is undefined. In the case of a square root, you can have an issue with taking the square root of a negative number, right? But in general, we say if there's no problems, then we're going to assume that the domain is all real numbers. Not all rational function graphs have asymptotes, but an awful lot of them do, and usually this is the first type of function where asymptotes come up for a student. So, looking at this abstract function here, we can see we have a horizontal asymptote at y equals -3. And we can also see that we have a vertical asymptote at x equals 2. Now these asymptotes are lines that the graph approaches, and whether or not the graph crosses kind of depends on the situation. With a vertical asymptote, the graph of a function cannot cross a vertical asymptote. To see why that's true, if we just imagine what would happen if this graph were to cross the vertical asymptote and turn around and still approach it from the other side, I can see that I now have something that violates the vertical line test, right? There's a little region right in here where I can draw, whoops, that wasn't very vertical, but I can draw a vertical line that intersects that graph more than once, right? So a vertical asymptote really can't be crossed by the graph of a function. With a horizontal asymptote, that's not true, right? We can see here that this graph crosses its horizontal asymptote and comes and approaches it from the other side. It's even true sometimes that you'll see a graph cross back, and actually oscillate back and forth. This won't happen with a rational function, but it is something that can happen with other types of functions that you may see later in your math career. So it is possible to cross a horizontal asymptote. But what you'll find is, regardless of whether the graph crosses, as you go out towards negative infinity in the x direction or towards positive infinity in the x direction, you'll see that the graph approaches these asymptotes. So it gets closer and closer the further out you go. Same thing happens with a vertical asymptote. As your x values approach a fixed value, in this case 2, your y values are going to approach infinity, right? So at a vertical asymptote, the function approaches infinity or approaches negative infinity. It grows without bound as you approach a number. So for our vertical asymptote, one way of saying this is that the function grows without bound as x approaches 2. With our horizontal asymptote, what we can say is that as x grows without bound, the function approaches a number, in this case -3. Meaning that there's a constant value that the function is getting closer to as you send x either out to infinity or to negative infinity.